Hello, everyone, and welcome to episode 42 of the Hyperthesis. I'm Patrick.
I'm Pheely.
And I am Liam.
Well, today we have what some would say is a slightly controversial episode for you. At least the theory behind what we'll be talking about is a bit controversial. And so we're excited for that. And I believe Liam will be guiding us through that conversation. But before we get started, does anyone have any intro topics that they want to discuss? If not, I have a cool topic to talk about. And that is something called environmental DNA. So environmental DNA, also known as eDNA, I'm realizing now that just spells out Edna, but I will be careful because I've flubbed acronyms and things in the past. Yep.
Was Edna the little lady in The Incredibles? Okay.
Indeed. Yes. No capes.
Is environmental DNA the DNA you get when you go to like a dirty club after it's closed and you just like take a swab of the floor?
I mean, yeah, that could be a place to get environmental DNA. I don't know how well you'd be able to differentiate between people there, but essentially that's the idea behind eDNA, is that you can just take a sample from, say, a body of water or a soil sample, or I've even read about an air sample that you can take, and then you essentially run that through a PCR process, or there are different ways, but the primary way is PCR processing, which we learned a lot about with the COVID-19 pandemic, where it's essentially able to replicate DNA quite rapidly, so you get a lot more of it. And then we're able to take a look at the different DNA that's within that sample and figure out what types of species were present.
Oh, I didn't. So it actually replicates DNA? I didn't know that was a thing.
Yeah.
Maybe that's
So
common.
So it's just a collection of DNA from environment. As when you say environmental DNA, it's like, well, you can't scrape a rock and have DNA because by definition, DNA was deoxyribonucleic acid, right? It's an organic material. So it's like environmental DNA sounds weird. So basically, it's just like, oh, we are just collecting DNA samples from places and grow it and then figure out what's there, like finding a trace of species.
Exactly. And that's why it is environmental DNA, because it's DNA that's been released into the environment. So, for example, if you're in a forest and you have a whole bunch of different animals that pass through one area, say, for example, on a deer trail, then you might be able to take a sample of soil on that deer trail and find the evidence of deer and ants and any different animal or even different plant species or fungi species or bacteria or whatever might have been there relatively recently, and you can show what was there. So it's kind of a way to count species in the wild, but using techniques that are kind of more related to genetics and these microbiology concepts.
So if I go outside during, pollen season, and I don't have allergies, so I can do that. I go out and I just take a swab of the air, and there's a million billion little bits of pollen. I'm basically breathing in the environmental DNA, but so I get a collection. How do I differentiate all these different plants? Like how do you like you said, the if you go to the club and after it's closed and you just take a swab of some mystery fluid off the ground, how do there could be a bunch of different people's DNA or a bunch of different plants or whatever, right? So how do you deal with that?
Right. So I guess the first thing is that people were all the same species. So that would require some more advanced techniques where think similar to something like a paternity test, where you can differentiate between specific gene markers that are able to say, okay, this is this person's child versus another person's. So that might be a bit more complex, and there might not be enough information there. But in terms of, say, finding out different trees, if you have, say, poplar and birch and maple, then those will have different DNA. This is something I'm still researching. It's actually going to be a part of my research, but you can differentiate between species, and there's active research into going, okay, how well can we differentiate between different species, and how close do the species need to be before it isn't as effective to differentiate between them.
There must be markers in DNA that help regulate that, because I heard, wasn't like saying somewhere like we are like 99% close, like same DNA as banana or something ridiculous like that, right? Like, so there must be the little part. I think that like those DNA have like more than 50,000 groups or something that like made up of like, the codec sequence. I'm not quite sure. But we are closer to autoorganisms in terms of like similarity in DNAs than we think, right? It's not completely different.
I think even like a tree, we're about 50% the same as a tree or something like that. We need to find a DNA scientist and get them in here and talk about it, because I know absolutely nothing about it, and you guys know a bit more than I do, but I think compared to someone who actually studies DNA, we know nothing.
Yeah, we'll have to get someone on here and stick around how you can find out how you can be on this podcast. But going back to eDNA itself, there are definitely markers that are present that you can look for, because to try and sequence an entire DNA sequence takes a while. Like, this was a huge milestone in the early 2000s, I believe, might have been the late 90s, where we were actually able to fully sequence the human genome. So to do that on such a large scale and try and do that for every single species would be extremely hard. But we can look at certain parts of DNA and determine, okay, this was a bird. Okay, it was most likely this type of bird, or this was definitely a tree. Because there are still significant differences between a tree and a person, for example, as is pretty obvious. But it's very interesting because this type of technology can be used for a lot of different methods, whether it's trying to figure out the presence of fish and which fish are present in a stream, which is important for fish conservation, or trying to figure out, say, how many trees species are in a forest, which is an issue that I'm very concerned about. And so this kind of general concept of using eDNA to identify different species and to tell what's in there in terms of diversity and maybe not so much quantity is called metabarcoding, or eDNA metabarcoding, which just sounds like a whole bunch of buzzwords, but it's really interesting how we're able to do this so effectively now.
So in your research, you talked about it about a year ago, maybe exactly a year ago today, actually, I think. Or were you number 3? Were you the second?
I think I was number 3.
Okay, a year minus a week ago today, we talked about your research in a bit more detail and how you used lasers from space to help determine different types of things going on in a forest, the different types of trees and things like that. So this is like a different way to do it. Another, well, maybe not. It's another way to potentially do the same thing. So like, how many different ways is there, and is there kind of like a standard one that's used, I guess?
I mean, there are tons of ways, in particular to tell the biodiversity. I just spent 2 weeks in Costa Rica trying to map trees so we can tell what species are where. But there are a very large number of ways, and as technology improves, we're trying to use different remote sensing methods to figure out biodiversity so we don't have to go into the forest or just kind of leave it up more to guessing of how many species there are. Instead, we're trying to figure out concrete methods where we can tell what species are present, and using this eDNA and then some satellite imagery, specialized satellite imagery. I don't know how much I can get into this because we're still writing the proposal. But essentially, we can use information about the DNA within the environment, and then some specialized satellite imagery, and see if they relate. And if they do, then we can say, okay, we can look over a broader area with satellites and kind of guess what the eDNA sampling would look like, and therefore the species diversity.
I guess what I'm wondering is that, like, if you use these combined methods to look at the biodiversity, you need kind of like a standard one that works really well to compare your results to make sure that they work. Or is that something you do or not?
Yes, that is definitely the case. And that's why we do field work, just
Hmm.
because we need to have that validation data and also testing data to make sure it works outside of the validation zone, um, to make sure that these processes work and find out which ones work. So we're able to look at sections of forests, or really any remote sensing scientist is able to look at specific sections, say, okay, what works in this specific section, and then try and apply it broadly.
Okay, my last question is which tree was your favorite while you were there this last time?
Okay, my favorite tree is called Indio Desnudo,
Oh,
which is, I wouldn't say the translation because it's a bit outdated, but it's a really cool tree where the bark peels off, um, and it's green underneath, and they are just usually, most of the ones I saw were massive. My least favorite tree, because this one's more interesting, is a tree that grows pretty well straight up and has very fine leaves, but it has spikes on it that are quite sharp, and I've drawn blood from it several times. But the spikes are hollow, and living all over the tree, especially in these spikes, are red ants, which when they bite you, it hurts a lot. So if you rub up against these trees, you get stabbed by the tree, covered in red ants, and bitten. So, yeah, it's a terrible tree. And
this
that's a cornusuelo.
does not sound like a good time, actually. Quite the opposite.
Indeed. Um, but does anyone else have any intro topics? If not,
Well, not exactly a topic, but I think I was in a theory club where my friend uh, gave a little talk about what the new thing called a continuous thermal majorization, and it's not. So I just want to bring it forward just to make you aware. But it's a new theory. It came out in 2018 or like 2013. It's like really recent, and it's a weird word. Thermal majorization. It's not thermalization. It's thermal plus majorization. Majorization is a mathematical process, I guess, like mathematical slash statistical thing you do to a probability distribution. But I won't go into that detail. And what they do is basically, how to solve non-equilibrium systems statistically, like in statistical mechanics. And instead of having isolated systems, you can have system plus environment, and how do you rederive the second law of thermodynamics from there, and how system evolve. So it is an interesting thing how maybe in the next 50 years, this theory will be developed enough for us to actually be able to use it or do something with it. So we won't be confined on the description of system in the isolated system anymore, or equilibrium system, which we know quite well how to describe those things. But maybe in the future, we'll be able to incorporate environment and describe how things work. So we'll see.
Yeah, I think that's what a lot of the that type of research, even not the specific one you said, like majorization or whatever, but there's a lot of people trying to figure out how do you deal with non-equilibrium systems, or like open quantum systems where you have, something and then you have this like
Exactly.
bath in the background. And open quantum systems are kind of nice. You can make big approximations with them, but sometimes those aren't good. So coming up with like a proper theory without any approximations can be hard, I think.
well, we will move on from that idea, which hopefully tickles your brain a little bit, I've never really heard of majorization, so I'm going to look that up afterwards. But we will now transition into our main topic, which is focused on the one electron universe or theory. So, Liam, take it away.
Alrighty. So we've brought this up a whole bunch before in the past, and we usually bring it up as a joke, the one electron theory or the one electron universe. I don't remember what we said about it, but I figured it's about time we have like a proper episode talking about it. So, I mean, if you've ever taken kind of high school chemistry, you'll know at like a simple level what an electron is, right? You have everything, well, mostly everything's made up of atoms. Um, so think of like a hydrogen atom, for example, has a nucleus made out of a proton and a neutron, and then there's this electron that orbits it. Your proton, your neutron are heavier than the electron. The proton is positive charge, the neutron has no charge, and the electron has a negative charge. So an electron is just a charged particle that is very tiny. Um, However, particles can have what are known as antiparticles, and for an electron, its antiparticle is called a positron. So it's identical to an electron, except instead of a negative charge, it has positive charge. So it has the same mass, the same physics, except now it has a positive charge to it. And when an electron and positron, if you take a piece of matter and a piece of antimatter and you touch them, they annihilate one another and just turn into energy. They turn into photons or light. So in quantum field theory, which is something we bring up all the time, but try to not get into too much, that's what quantum field theory describes that process. So today we're going to be focusing on this so-called one electron, like we said, one electron universe, the one electron theory, which was an idea proposed by the physicist John Wheeler in a telephone call to the other physicist Richard Feynman. So Richard Feynman's a pretty famous physicist. Most people have heard of him, and I think most physicists have heard of John Wheeler in some form or other. Maybe they haven't, but he's a well-known name for physicists. And he had this idea that all electrons, so in our universe, you have all these electrons everywhere at any given instant in time, and they're all identical. They all have the same mass, the same description, the same charge. And then you can also have positrons, except with their positive charge instead of their negative charge. And Wheeler was trying to convince Richard Feynman that what if all of these different electrons that exist in different points in space at some given time, what if they're all just the manifestation of a single particle, a single electron, but this electron can now move forwards and backwards in time. So this electron it zigzags backwards and forwards in time. And at any specific like kind of instant in time, if you take a time slice, all of those different electrons are just a specific point in the trajectory of this single electron that whizzes around the universe backwards and forwards in time. So that is the one electron theory or the one electron universe. It's that we don't have a bunch of electrons that are identical. We just have one electron that zigzags around the universe on this crazy trajectory going forwards and backwards in space-time. And at a specific in a specific instant in time, it represents every electron that we see.
Also, I think it's posited that when you travel backwards in time, it manifests as positron, right? Or something like that. So like the antiparticle of the electrons are basically itself turned backwards in time. Pretty out there.
That's the idea. So that when the electron's moving forwards in time, if you take an instant in time, it's an electron. But if it's moving backwards in time, you take an instant in time, that's a positron. And that's something I'll talk about a bit more soon, actually. So it's a pretty wild theory. It's a pretty bold claim to say that every electron in the universe is just one of them. Actually, every electron and positron in our universe is just a single one. So the kind of motivation for this was that I don't know if this is something physicists still care about. I'm sure some people probably do. But back, I forget what year it was, but 1940 roughly. physicists were wondering why every particle is identical, or why every electron. So the electrons were like one type of particle. They were wondering why are they all the exact same. Um, there was nothing in their physics that explained to them why that would be the case. That was the motivation for this theory, because if they're all one electron, then well, that explains why they're all the same. So yeah, pretty bold claim, pretty wild theory when you first hear it, and I agree, because we always joke about this in the past. We bring it up that maybe there is just one electron. The short answer is that no, there's not. There are many electrons, and I'll explain that a bit more. But in physics, even when something seems completely ridiculous, if at first glance the math makes sense, you shouldn't throw it out. And even if it turns out to be wrong, it can lead to deep insight. So
You don't sound like a true believer.
I'm not a one electron supremacist. I'm sorry. Because like intuitively it makes no sense, but it turns out there's a reason why it doesn't. It's not just there's a reason. I mean, our current theory doesn't make sense with the one electron theory. But at first glance, the one electron theory is mathematically viable to some extent. And it's like general. I always bring up general relativity. How people, when Einstein first proposed it, he's like, "Oh, your time is relative. Different people see different times depending on what they're doing or where they are in the universe." And people there's this like famous example, and I'm sure I've said this before, but there's like a series of papers published or a book or something with 100 people claiming to disprove Einstein, and he simply said, "If I was wrong, there only need to be one paper to disprove me. There wouldn't need to be 100 of them, right?" So even when something seems completely ridiculous in physics in our universe, it turns out that sometimes it can be correct, or maybe it's partially correct, or maybe it leads to deeper insight on some level.
I think it raised the question of like what is a plural, right? Like how do you define things being singular? This is also more of a metaphysical sense, but like how do you say there are two things when that now, but well, you can you observe two things at a time, which kind of reminds me of this playable teaser of a video game that never came out. The teaser came out 2014. I know you ever heard of PT. It's like a playable teaser for Silent Hills. The first sentence, the first line, first couple lines was the "Watch out, the gap in the door is a separate reality. The only me is me. Are you sure the only you is you?" It's like, wow, that's deep. I don't know how that leads to the one electron theory, but it's to me is question, like how do you know that one thing is distinct from another?
Yeah, I guess, I mean, on a deep level, you don't. But the way I'm thinking of it is that, like, if you have, you have like two baseballs, and you throw them in separate directions or in random directions, and you trace out the path they took, their trajectory, you get these two different lines. Um, those lines will never have started at the exact same point, and they won't end at the exact same point. But if you threw one baseball and looped it around a bunch, it and then kind of ignored where it started and ended, it would look like you'd have separate trajectories. So I guess yeah, instead of having a bunch of different particles following different trajectories, it's like you have one particle that kind of loops around through all those trajectories. Like that's the way I'm thinking of like a separate entity, is that the one electron's connected everywhere, whereas the individual electrons, I guess they'd only be connected like through the Big Bang, maybe at the beginning of the universe.
Well, the simultaneity is a problem here, right? When you say at the same time, I could say, well, I'm the different observer. I see them completely different, just one particle, just travel in this one trajectory because you observe it different way. You saw like it's like cut off. That like this at the same time it's not. But
Well,
I'm
that's
sure there are
one
arguments
yeah,
against that.
that's one problem with the one electron theory. Actually, is that um, in quantum field theory, in curved space time. So if you combine gravity and quantum mechanics, it turns out the definition of a particle is not this absolute thing. One person can see a particle, a different person moving on some different trajectory or near a black hole or whatever, they won't see it. So different observers can see particles. Well, like that's what Hawking radiation is. Someone far away from a black hole sees particles, someone near a black hole doesn't. And so like these things I've talked about before, like the Hawking effect, Unruh radiation, those are all examples of different. The vacuum of space may not be the vacuum of space to someone else, and that's kind of the one electron theory. I don't think is really compatible with that. Although I didn't do the math and I didn't see this talked about anywhere, but that's what it seems like to me, at least.
Well, if you basically redefine particles as more like a undulation or fluctuation in the like ever existing field in the observable universe, then then isn't there just should there be just one field or one
Yeah.
thing, and you just there's like a fabric. I don't want to say fabric, like some kind of field, right? If particles are different modes of that field, maybe I use the word mode loosely, then maybe it's just like just there's just one field to
Yeah,
rule them all.
So the one electron theory kind of preceded the development of quantum electrodynamics a little bit, which completely changed how we think about the universe. So quantum electrodynamics is combining electromagnetism and quantum field theory. And we've talked about this before. I say that so many times because we have, but this is like in QED, there's the fundamental object. So if you want to describe electrons, the fundamental thing is not the electron itself. It's called the electron quantum field, which is what you just said. It's this like kind of all permeating thing we can't see that exists everywhere in the universe. And the electrons are just excitations in that. The fundamental object is actually the electron quantum field vacuum. So it's the stuff we can't see. It's the absence of a particle. That's the fundamental object in quantum electrodynamics. And the electrons that we see in the universe are actually just excitations of that. So quantum electrodynamics actually kind of tells you why are all these electrons the same, because they're just vibrations, that they're specific vibrations in this all permeating electron field. And then positrons are they have their own quantum field, the positron field. Or they're all right, that's something I have to double check that. I kind of forget now. There's so much math that I've done in the past, I get confused sometimes.
I will just point out there's another famous, I guess more famous field that more people may have heard of, and that's the Higgs field. And again, it's based on the idea of quantum field theory, where it's this kind of all present, all permeating field where it's just kind of present everywhere, but the excitation of the Higgs field is the Higgs boson. And as someone who did particle physics, they essentially any particle that you have, according to quantum field theory, is just an excitation of whatever field it may be a part of. So, for example, quarks are excitations of their own individual quark fields, or however that works. And same with electrons and the electron field, any types of different bosons and their boson field. But yeah, if you've heard of the Higgs boson, that's associated with the Higgs field, which also might give mass through the Higgs mechanism and all of that. But there's a slightly more famous field.
Yeah, so the universe is just all of these different quantum fields kind of overlaid on top of one another, and the electron has its own specific field. Does it include the positron? I think it does in that field. Or is a positron its own field? I think when you actually do the calculations, so for the physicists out there, you actually have separate creation and annihilation operators for matter and antimatter. So I think it's its own vacuum, it's its own quantum field, but don't quote me on that. Anyway, we can move past that.
Who knows? Which reminds me what you just talked about, that a meme I sent out to my theory club this past week. There was like this picture of, I think, SpongeBob representing high energy particle physics, but experimental, like playing with the Higgs boson. So you're like some object, and then there's Squidward, which is high energy particle but theory. Have all these clocks, like he's playing with graviton, dilation, second Higgs, stop quarks, all these things, which is like, well, I mean, it's open another can of worms, right? Like if everything is just excitation of the arbitrary field that you can just define. I found that a particle is just a different field, just maybe different number, and I don't really subscribe. I don't like that model that much, but maybe it's a very good. I think it's a very good description, but it's give me that vibe of the string theory. That's like, okay, all right, man, this is too over encompassing. That might not be true. Too good to be
Yeah.
true.
Quantum field theory and quantum electrodynamics work really, really good in the sense that we can do experiments that justify them. It's not like string theory in that sense. So we know it works really well. And, we don't have a complete theory of quantum gravity, so they're not quite fully correct. So there's something we're missing, something big, because we've been trying to figure it out for, 100 years or so. And well, not quite 100 years, maybe like 50 years or something, but
Yeah, I don't think we have like good competing theory that fights it, because like to do experiment, like you said, you can test doing experiments and stuff. But what if the test results go the other way, right? Is there another theory that kind of support the other side of the claim? Because like before, let's say like photoelectric, right? Like before, if we didn't believe that photons can be particles and behave the way that Einstein like posits, well, maybe it would fall into auto theory, right? Is there another theory that if QED are not true or found not to be true, that could be a very convincing theory against that? I know one electron theory is not exactly convincing, but maybe I'm not sure if in the literature right now if there is any theory that on that level of QED. I don't think I know of any.
yeah. So QED, I mean, that's QED is really good. Like when you do the experiment and you measure something, QED is like accurate to within 10 or 20 decimal places or something stupid. But again, you're right. We're missing some higher theory. But that higher theory, because we know QED works so well, that higher theory, QED kind of has to drop out of it in a specific limit. So coming back to the one electron theory, turns out, yeah, that's why it doesn't. Well, according to our current theory, it doesn't really make sense. Because electron's not the fundamental object itself; it's the electron quantum field. So it no longer really makes sense to argue that there could be a single electron because the number of electrons isn't it's not a conserved quantity, according to at least according to quantum electrodynamics or quantum field theory. And then there's that other issue I talked about with how different observers can define a particle to be a different thing, or they see different vacuums. However, so what does it? So there's one thing I could talk about now, but I'll maybe change the order of how I want to talk about things. So even though the one electron theory has some flaws and doesn't match our current best description of nature, like any theory in physics, it's always good to explore it a bit because maybe it could make a rebound, or maybe we were missing something, or maybe it leads to some useful insight. And the one electron theory, which I didn't actually know, it led to kind of Feynman developing quantum electrodynamics, or being one of the people who did. In that John Wheeler phone call with Feynman, Feynman actually he thought there were some flaws in the one electron theory. But he actually used this insight that antiparticles could be represented by reverse trajectories of their particle counterparts. So he said, and I'll come back to what that means in a second, but so Feynman said in his Nobel Prize winning speech for the development of quantum electrodynamics, he said, "I did not take the idea that all electrons were the same one from Wheeler as seriously as I took the observation that positrons could simply be represented as electrons going from the future to the past. That I stole." So in quantum electrodynamics, you can mathematically represent an electron moving forwards in time as a positron moving backwards in time, or or vice versa.
Yeah, as a statistical mechanics person ish, like I find the idea of things travel backwards in time really, really got on my nerve because I don't think that's how it works. To me, those are mathematical tricks, right? If someone tells me I can multiply better, I have a trick, you multiply this way. This works. You can get to the answer faster. That's to me, those models are, right? Like to me, well, particle is not actually going backward in time, but our conceptualization that we have that abstraction helps us understand the behavior better, to describe it better. Doesn't necessarily mean it does that. And yeah, I mean, it's an interesting insight, and I think it's necessary insight to do that sometimes. But to me, it's like always have to recognize that it's not really a thing. It's just a trick. It's a mental trick. It's an intellectual trick. It's a mathematical trick. Whatever how you say it.
Yeah, I think you're right there, actually. Feynman's famous for being the guy who said, shut up and calculate, because during his time, quantum mechanics was really this huge breakthrough thing, and no one understood it. But we knew that it worked because it matched experiments. We still don't really understand quantum mechanics on like a really deep level. We just know it works. And same with quantum field theory. We know it works. We know that there's these quantum fields, but like we don't quite know what that means. Or even like this particle is a anti-particle traveling backwards in time. It's not, as far as I'm concerned, and I have some more to say on that, but as far as I'm concerned, yeah, that doesn't really make sense. It's just kind of, I don't want to say it's a trick because maybe it's not, but we can't ever test it because we can't go backwards in time because of entropy and all that jazz. So it's more of like a math thing, as far as I'm aware.
Well, Feynman to me is a king of tricks. I mean, like he wrote a book about it. I mean, he wrote books about it. Right? Like Feynman diagrams to me is a trick. It's a very good trick. I mean, particle is not exactly moving in a line or like doing that jazz, right? But it's a very good trick to calculate certain things. And like I think through his life have been finding tricks to calculate things faster, to understand things. Rename sine and cosine, change symbols, picking locks, or finding tricks, all the things, how to explain things in a way that novel and in a way that more intuitive, right? Tricks, to me, tricks are tools to make like things that really hard to understand intuitive. That's why to me it's called tricks. Like, oh, what are the tricks of doing derivative? Like to me, tricks are just like the way to tell people how to intuit derivative instead of the conventional connotation of tricks, which is more like trickery is a bad thing, right? To me, trick is amazing. Tricks in mathematics help many people. Like I have tricks to calculate common angles, sine, cosine, and tangent for common angles, and students love them because like why don't they teach them in school? Like they're just tricks. Like to me, that's not just tricks. There are like sequence of intuition that you can teach people.
Yeah, one thing to be said is that in many cases, I like to think of tricks as approximations, which isn't always true, but it's often true. Like, I mean, Feynman diagrams for the physicists out there. Feynman diagrams are just perturbation theory, right? Like that's just a mathematical approximation because you have an equation that describes your system. You got it from some way or another. You got it from something that makes sense, but now you don't know how to solve it, so you do this thing called perturbation theory to solve it. And I won't get into it, but Feynman diagrams are beautiful as hell because like they just describe each order of perturbation mathematically. So yeah, they are a trick, but they have some mathematical justification behind them. But so what does it even mean, right? What does a particle moving backwards in time mean? And like we said, it's not really, as far as I know, it's not really a physical thing. It's more of a mathematical trick or equivalence. It's really related to this thing called time reversal symmetry, which I won't get into too much. So in quantum field theory, particles carry conserved quantities as they evolve through the universe. So by conserved quantity, I mean it's something that can't change over time. So imagine you have like a hose, right? You put water in one end, and assuming none of that water gets stuck to the inside of the hose or the hose has no leaks, all of that water will come out the other side. The water can't magically disappear on its way from one end of the hose to the other. So the water would be a conserved quantity in that case. The mass of the water would be. So so if you have like kind of, for thinking more physicsy, if you have like particles, as a particle moves through the universe, it could have different conserved quantities. It could have like charge or energy, momentum, and there's all these other kinds I won't get into. So as the particles move, these conserved quantities produce currents, and these currents have a direction based on motion, based on their motion and the sign of the conserved quantity. So if you think of an electron, so this is the obvious example. If you flow an electron through a wire, it creates a current. So if you know anything about electronics, you know that that's what current is. It's a bunch of electrons moving through a wire, and they move really slowly, it turns out. But that's what happens when you flick your light switch on. You're creating a current that goes through the light back.
Well, I don't think that's true. The drift velocity is different. Electron itself, I believe, is moving really fast.
Oh yeah.
But the drift velocity is not the speed of electrons. It's a collective speed. You know, it's to me, it's like it's not really a thing. It's like a mathematical trick again. You know, there's nobody measure the speed of electron really, right? Like it's not like you can. I mean, I guess you can, but like it's not done in a wire.
Yeah,
So
like,
it's a trickery that works.
well, it's not. I wouldn't say it's a trickery. I'd say it's an average thing, like the average motion of the drift velocity of the electron. It's an analogy. The point is that flowing charges create a current. So conserved quantities, when they flow, they create some kind of current. So you can think of like an electron moving through space-time as having some charge current associated with it. And this is where this particle-antiparticle analogy comes in. So if you were to what's called time reverse the electron, so imagine that you stopped time and then reversed it so that this electron's now reversed its direction and it's moving backwards, moving the opposite direction. That's equivalent to actually just reversing the sign of the charge. So if you have a bunch of negative charge going one direction, if you reverse time and it moves the other direction, you can describe that as a bunch of positive charge moving one way. And that's called time reversal.
Yeah, well, I guess so. I mean, time reversal symmetry is I think pretty straightforward. In a way, it's like, like, oh, if it go opposite way, it should have opposite properties. I think that's like an easy way to like conceptualize it, right?
Mhm.
Like it's like, well, if I run forward in time, you know, I'm gonna look like who I am now. But if I run backwards in time, I'm gonna look like the opposite of me running forward.
Yeah, it's a really intuitive thing. It's like, if I throw a baseball and it goes this parabolic trajectory, if I were to reverse time, it would just follow the parabolic trajectory back to when I threw it. It kind of makes sense. So with these charges, right? If I have an electron moving from left to right, it has a negative current because it's a negative charge carrier. But if I reverse time and it goes back to where it started, that's kind of like describing a positive charge moving from left to right. It's mathematically equivalent, and that's where this whole idea of a particle moving forwards in time can be considered an antiparticle moving backwards in time. That's kind of like the hand wavy justification for it.
Uh, Two things. One, I will just mention that if you want a cool demonstration of things moving backwards and forwards in time, and you have a Nintendo Switch, check out Tears of the Kingdom. Fun game, but yeah, you'll know what I mean if you've played it. And then the other thing is that we're talking about the existence of these positrons and the fact that backwards flowing electrons are the same as positrons, but where are all the positrons? Where's the antimatter?
So that's another thing I completely forgot about. Thank you for reminding me. The one electron theory does not talk about that, but most of our current theories don't either. Is the antimatter asymmetry of the universe. So the fact that when the Big Bang happened, according to like, I don't want to say every theory because this is a hot topic. A lot of people work on it, but according to like the kind of first theories we came up with, the theories of like inflation and the Big Bang, there should have been equal parts matter and equal parts antimatter. So why is it that we're all made of matter and we don't really see antimatter anywhere? The one electron theory doesn't take that into account because you would expect from the one electron theory, roughly, you'd have equal parts matter, equal parts antimatter. But also, then again, like our other theories of quantum gravity, we don't have an answer for that yet anyway. So
Well, it could also turn out this is going to be out there that dichotomy of matter and antimatter is nonsense too, right? Like it could be in the future, like, well,
Mhm.
there's no such thing as antimatter; it's just another type of matter, and that the fact that it carries positive or negative sign in mathematics might just be an error. Who knows? And because maybe we haven't, well, we know that we haven't found that much about dark matter and dark energy. We have a lot of dark matter and dark energy around. We don't know what they are exactly, right? So maybe there's something that has to do with antimatter, maybe not, right? Who knows at this point? But my point is that our current theory that conceptualized matter and antimatter is not perfect either. I don't think it is. The fact that charge is positive or negative, when you look back at the argument that things are just excitation of things, well, then what is positive, negative? Where is zero? Can zero be shift? Then when everything will be positive, right? If it will say charge is -1, well, what if zero is at -1? Well, this is a weird rant, but mathematics don't work exactly that way right now, right? But it could be a way. I believe that it's conceivable to create a theory that could do that. Maybe operations of add and multiply, like adding and subtracting, is not the best. Who knows? But this is getting to the wacky realm. But I want to point out that like the current theory has its flaw, right? So we are not sure. Maybe the fact that we are hopefully close to tap into dark matter and not very close to dark energy, but the fact that we are somewhat near that might be able to shine some light on that issue on matter and antimatter dichotomy.
Yeah, I kind of lost you with the whole the whole charge thing a little bit, but I kind of see what you're saying. But just to wrap things up, there was this. I have a friend like years ago who had a kid, and their kid I think was like 6 or 7, and he made a Facebook post about a quote his kid said, and his kid said something. It was something like this. I'm paraphrasing, but it was basically like, scientists call their guesses theories because they want them to sound important. And I thought that was so funny because it's like, yeah, it's basically just it's an educated it's not a hypothesis, it's not an educated guess. It's a bit more than that because you have some evidence and you've done some math and some experiments, but it's effectively just a very good guess. And we don't have a complete theory of everything because we have things that aren't described by our theories. So then you yeah, like you say, you come up with new theories that contradict everything that you originally thought. Sometimes they do, sometimes they don't, and they solve your problem. Like that's like quantum mechanics and general relativity. Those came in and they said classical mechanics, you're pretty good, but you don't make some sense sometimes. So
Yeah,
yeah,
I would go so far as to say it's the best guess humanity have.
yeah,
It's not just a good guess. It's not just educated guess, right? It's a collective best guess that we have.
and that's exactly what quantum electrodynamics is right now. It's the most experimentally verified best guess we've taken. And even if the one electron theory was not our best guess, it was a good guess, and it helped lead to the development of our best guess. Best guess, not guessed. Too many words in one sentence. So yeah, that's the one electron theory in a nutshell. I don't know if there's current research in this. I just kind of found this information in some old websites online, like Wiki and things like that. But maybe there's still people who study this.
Imagine trying to go get funding to research it and you have to write a proposal. It's like, I want to study a one electron theory. Good luck getting funding, buddy.
Well, if you happen to have funding for studying the electron theory, or you are another person who's a best guesser, aka a theoretical physicist, um, and you want to be on our show, you can contact us many different ways. You can send us an email. We're hyperthesispodcast@gmail.com. You can reach us on Instagram. We're at the Hyperthesis, where we post updates and memes and whatever else we feel like posting that's related to the podcast. And so you can send us a direct message over there. And again, if you are an expert in your field, we would love to have you on the show, whether it's theoretical best guessing or theoretical physics, or you're a biologist, chemist, heck, even an engineer if you want to come and talk to us about something cool. We will be more than happy to have you on here. And we're always very curious about learning about new topics. Now, in terms of listening to us, you can listen to us pretty much on any podcasting platform. We're based out of Spotify, but we are on Apple Podcasts, Google Podcasts, Amazon Music, and again, wherever you get your podcasts. We are also on YouTube. You can check out our very cool YouTube videos. They were done by Pheely, and the animations are pretty cool, but you can also listen to full episodes on there. And wherever you listen to us, make sure you give us a like, a subscribe, or if you want to message us feedback, feel free to do so. We are always keeping our eyes open for how we can improve or what we can do differently, along with, again, if you want to be a guest and you're an expert in your field. So like, subscribe, do whatever you need to do to listen to this podcast, share this podcast, and get into contact with us. So to end today's episode, we will be hearing another number-related story, this time from Pheely.
All right. So for today, we talk about one electron theory. So I want to talk about the history of number one, really. I took a lot of this information from the documentary from, I think, 2005 by PBS, hosted by Terry Jones, on the story of number one, or story of one. So, as we all know, or familiar with, number one is probably one of the most fundamental thing to counting, to human life, right? And when you have something, do you have something, one thing, two thing, or not have anything? At least for us in the modern world, such concepts become so intuitive, right? It's easy to us to imagine 1, 2, 3, 4, 5. Well, I guess that's one of the power of education, which is quite nice. However, this has not always been the case. Zero has not been around that long. Actually, it's been around pretty long, but not that long. So how old is one? It's really tough to put a number of years on that. It might be impossible even. I mean, archaeologists has some trouble locating that. I mean, how do you prove that when people start counting? So, but at least in the Congo, it's been proven that it's around for at least 20,000 years from like a notched bone they found. It's called Ishango bone. So around really 6,000 years ago, when the Sumerians have like a token, a cone-shaped token, and turn it into first ever numeric character, that invention that really made arithmetic, so the study or method of dealing with numbers, and so allows city life to be possible because it provides the means to access wealth, calculating profits and loss, basically money, including taxes, right? So before, you could imagine people barter, just like, oh, I have a goat, you have water, let's trade, or something like that. There's not really a good way to count if you don't know how to count or how to add, subtract, multiply. You just look at it and, well, that seems fair. But when you have a bigger society, that might become problematic. So first numeric thing started around 6,000 years ago. However, a few thousand years later, I think only 1,000 years later, in Egypt, so we found the first use of million, which is a quite large number at the time. So as well as the invention of measurement. So one could be also thought of a unit of measurement. Like, what is one? Well, is it 1 centimeter, 1 meter, 1 foot, 1 yard? So the Egyptians created their own version of one. So it's called the cubit. It's an ancient unit of length based on the distance from the elbow to the tip of the middle finger. So that is one unit when they want to build something, right? So further on, it comes to, of course, the Greek. So in ancient Greece, so one was actually quite important and held at high regard. So Pythagoras really loved studying one, and some could argue he lost his mind trying to study the number. And Archimedes was also absorbed in one, and also diagrams that also that he lost his life from the Romans when they came to invade. However, the concept of numbers and stuff has kind of halted a little bit at the Romans because they do love to fight. So one became a tool of the order because Roman numerals, the letter I, as we know it, the capital I, becomes a number, the number one. Even though Roman numerals, as we know in modern worlds, is not really practical. When you want to add stuff, when you want to multiply, Roman numerals just really bad at it. Imagine try to multiply things in Roman numerals. There isn't even zero. There's no zero at all in Roman numerals. So how do you deal with that? Even though as bad or well, quote unquote bad as it was, it's dominated Europe for the next 2,000 years. That's quite a long time. But changes came eventually. It began in India, of all places. So in India, where the symbols of 1 through 9 were invented. Also, it's the first use of zero. And, well, even though we are familiar with the Arabic number, it's actually the full name is the Hindu Arabic number. It's also because it first invented in India and carried along to the Arab world where it was really formalized. So let's go to the Arab world. So in Iraq, in the Baghdad, where the Muslim scholars were studying 1 and 0 extensively, these things are, well, even though they study 2 and 2 to 9s as well, 1 and 0s were particularly tickled their fancy. So the most famous Muslim scholar, Al-Khwarizmi, and his colleagues taught these performing numerals more tricks so like how to add them, how to multiply. So these feats enable science, mathematics, and everything else, astronomy, to reach new heights in the Middle East. So if you look at the history of mathematics and all the tools, astronomy, or even astrology is rich in the Middle Eastern, in the Persian Empire, basically, right? Persian Empire used to almost dominate the world, or one could say dominated the world for a while. And you look at the historical artifacts that came out of the Persian Empire, are one of the most precise, beautifully made, great craftsmanship. So, in fact, Al-Khwarizmi, Latinized name, you're going to be a little surprised, algorithmus, turned into the name of the method used for computation and survived until now, known as algorithm. So it's after the name Al-Khwarizmi. So all algorithm used in computers, mathematics, just let you know, it came from the root of this word. That's why actually one of the reason I love studying etymology, which is study of the origins of words. I don't study it extensively or formally, but I like to look at it as a hobby. Anyways, Indian numbers were a hit. They were everywhere. Well, I mean, across the Islamic world before it came to Europe, where it actually met with quite a strong resistance. It took 500 years for the Romans and Indian numbers to play out. But by the 16th century, the Indian figures, now known as the Hindu Arabic numerals, finally won. Maybe because the Florentine mathematician called Fibonacci showed the Christian merchants how to use Indian numerals to calculate profits and losses. Well, when money got involved, well, you better change the number, right? Because if you want records everything in Roman numerals, maybe you won't be as successful as the Arabs. But the story really doesn't end there. Within 100 years, German mathematician Gottfried Leibniz invented a binary system using the origin of mathematics, the 1 and 0, which one could claim that is the birth of modern computers. Well, not the modern computers, modern computation, and which give rise to computer, it was one of the story we talked about with Alan Turing and how he developed first modern computer. Well, these type of numerals 1 and 0 help that us to replace the abacus, which is like the ancient tool to ancient calculator. I think invented by either the Chinese or around there, right? So it's very, very good way. So that is the very brief story of the number 1 and how important it is to realize that, well, it's not so intuitive to be able to think in 1 and 0 up until recently, relative to the very long human history that we are able to intuit this. And I hope my story shed some light onto some concerns or fleeting thoughts or dreams that some people may have.
Well, thank you for that wonderful story, Pheely. And if you too are interested more in the history of the number 1, it's an excellent documentary that Pheely mentioned at the beginning and worth checking out. But if not, that was a very good description on the history of 1.
Oh, there's also a really good PBS Spacetime video on the 1 electron theory. I would recommend it if you're interested.
Yes, well, maybe experiment with putting some links in the description. But now that the story is done and we've discussed possibly our most controversial topic on the show, or some would argue, thank you very much for joining us for episode number 42, and we'll see you all next week. Bye, everyone.
Godspeed.
God bless.